reach out by chat. And then either during the presentation if you have questions or afterwards. So I first just want to say thank you to some really incredible students and postdocs and undergraduates that I've had the pleasure of working with. And right now, I think we really live in some incredible times for artificial intelligence, and in particular reinforcement learning. Over the last decade, we've seen reinforcement learning systems that can beat human experts at video games. We've seen reinforcement learning systems that can do incredibly well at complex robotic tasks, as well as beat the world champion at Go years before it was expected to be possible. But I want to introduce a challenge that I think probably most people and most academics in the audience are familiar with, which is the challenge of office hours. So if you think about starting and providing office hours for the first quarter of a class for a new homework assignment, you really are doing a very complex decision-making process. You're dealing with partially observable state because you don't know what the student understands or doesn't understand. You're trying to learn quickly and take a sequence of decisions to help them reach that understanding. You're frequently under time budget constraints because you want to help the next students as quickly as possible. And you're trying to figure out strategies that work well, not just for one class of students, but really for all types of students. And I think at this point, we don't have any reinforcement learning systems that are capable of doing the task that pretty much all teaching assistants across America can do from the very first time they start teaching. And so in addition to the fact that it's a key challenge for humans, it's really a key challenge for science. One of the first people in reinforcement learning, thinking about multi-arm bandits for clinical trials, argued that even though it seemed like it was going to be an incredibly challenging task to reason about making decisions under uncertainty, that it was nevertheless likely to be pivotal, both for sort of mathematical statistics, but also for the implications for science as a whole. And so the reason that I'm interested in sequential decision making is that I think that quickly learning to make robust decisions is a key part of intelligence. It's something that people can do effortlessly. And I also think that it's critical because it's going to be core to advancing AI for human benefit. And if we want to be able to have reinforcement learning systems that can tackle problems in education and healthcare, I think it's critical that we have good solutions. So what I'm going to illustrate briefly now is three sort of high-level challenges that this promotes, and then I'll dive more into them in the rest of the presentation. So the work that I am going to do and talk about throughout today is really characterized under this general umbrella of how do we learn from limited samples to robustly make good decisions. So one example that many of you might have heard about in the news from the fall is some really incredible results from OpenAI, where they managed to have a robotic arm that can manipulate a Rubik's Cube. And one of the notes they make in that paper is that it took on the order of around 13,000 years of compute for them to learn how to do this. And if you do a quick back of the envelope calculation, you might estimate that what they needed is around 197 million attempts for their robotic hand to learn how to do this task. Now, this is clearly way more than any human needs in order to learn to do that task. But you might wonder whether or not that's reasonable, because maybe we'll have that sort of data for the types of applications we need. Unfortunately, if we think about cases that we might want to tackle in the real world, we might want to tackle things for humans involving things like how do you help people with fitness goals, then let's think about a particular type of device. In particular, if we think about something like the Fitbit, there's only been about 90 million of them ever sold since this company was launched. And Fitbit is one of the most popular exercise support devices out there. And so that argues to me that if we're going to want to be able to use reinforcement learning algorithms where we don't have access to good simulators, and we're going to rely on real data, we're going to have techniques that can learn from limited samples in order to robustly make good decisions. Let me say a second challenge. The standard paradigm in reinforcement learning involves agents that can take actions and get back rewards, see state information, and then use that to make new decisions. And we typically refer to that as online reinforcement learning. And that's really been the dominant paradigm in the field for the last 30 years. But I'd like to argue that there is a huge opportunity to think about a slightly different form of reinforcement learning, which is batch reinforcement learning. So just to give one example, if we look at the American Reinvestment and Recovery Act from 2009, this was really one of the major instigators for why hospitals now have and collect enormous amounts of electronic medical records about decisions made and their outcomes. And some estimate that there's now around 2 × 10⁹ gigabytes of healthcare data about these sorts of decisions that are being made. And to me, this means that there's this enormous opportunity to leverage these sort of data traces about decisions that are being made and their outcomes and use them in order to make better decisions. And if we want to do this, we're going to have to deal with batch data where it's been collected with an existing process. And we want to be able to make robust, good decisions that we have confidence about before we deploy them. As just a third example, one of the first instances of using reinforcement learning for intelligent tutoring systems was a system that was developed in the late 1990s. And what it did is it helped students learning about math, and its objective, its reward function, was to try to help students to do problems quickly. Now, that might be one reasonable objective. There's a lot of limitations to it, but I think it's useful to compare that to say what the Palo Alto School District, where one of my sons goes, what they state is the goals of their education. So this is only one page of their stated goals for the school district and the goals of their education. And if you drill down into it, it includes things like ensuring that all students are going to perform at or above grade level, but also much more complex objectives like helping students to discover passions or to promote equity. And so if we think about using reinforcement learning to quickly and robustly learn to make decisions, it's critical that we think about what those decisions are and what does it mean for decisions to be good. And so together, this has sort of been the major focus of my own work. And to tackle these problems, I think about sort of 3 different types of forms of research. So the first is thinking deeply about particular application domains, particularly in intelligent tutoring systems and in healthcare. The second is to think about how do we develop general tools to advance our understanding of reinforcement learning and also to build algorithms that people can build on. And the third is to think strongly about theory, because theory gives us a way to sort of ground and solidify our understanding and to understand whether or not what are the limits of how well any system can work in these types of decision processes. Okay, so today what I'll be doing is talking about this general goal of how can we have systems that learn from limited samples to robustly make good decisions. And before I do that, I'm going to give an incredibly brief introduction to reinforcement learning. I suspect most of you are familiar with this, but just to be clear on notation, I think about systems where they take an action A, they will receive some reward back and some state information, and we're trying to learn to map to go from observations about the world to actions. And most of my work thinks about Markov decision process reinforcement learning, where we think about there being an explicit dynamics model that governs how states change and reward models, and that the typical goal is to maximize the expected discounted sum of future rewards. So the first thing that I want to talk about is this sort of first challenge that I mentioned of how do we learn from limited samples? And this challenge of how can we quickly learn is something that we've been doing a lot of work on over the last decade. And I'm just going to focus on one aspect of this, which is sample efficient reinforcement learning in tabular domains. So I'm very happy to answer questions about any of the other aspects, or feel free to contact me later. Now, this challenge of reinforcement learning with little data and thinking about what are the sort of fundamental performance guarantees we could hope to have with reinforcement learning systems has been something that's been thought about since almost the start of reinforcement learning in the computer sciences. And yet, this has been sort of a long-going outstanding challenge of just how good can reinforcement learning systems be, and what are the limits of the performance? And one of the things that we've shown recently, as sort of a cumulative build of a number of years of work, is that we've now closed one of those problems. So for perhaps the simplest setting that's still meaningful that we could imagine trying to make progress on, for tabular episodic settings, we now have mini-max bounds. So we can say formally, in the worst case, this is how much information or how many mistakes an agent would have to make in order to learn to make good decisions. So to back up for a second, I think it's helpful to refresh what are the formalisms for how do we assess a reinforcement learning algorithm. So of course, one common way is empirical performance, but I want to have guarantees on how well systems are going to do before I deploy them in a new environment, particularly for these types of societal applications I care about. So if we think about an agent that's making decisions, we could think of there being a series of episodes, say a series of students or a series of customers or a series of patients. We could look at how well the algorithm performs. And then we can do that across a series of episodes. And our hope is that over time, the algorithm is generally learning to get higher performance. And imagine that we could compare this to what is the optimal expected return that the best algorithm could get in this domain. Now, if we compare the difference between how well the algorithm is doing and what would be that optimal return, we get a series of gaps, and we call that the regret. We call it the sum of those differences is the regret, which is the difference between how well the algorithm is doing and how well it could have done if it was making optimal decisions. And in the context of high probability regret bounds, we like to bound how fast this is growing over time with a number of episodes. Now, in some cases, you may only care if performance isn't near optimal. And so the other dominant paradigm for thinking about assessing reinforcement learning algorithms is thinking about counting up the number of mistakes, the number of times the algorithm made decisions that were not near optimal. And this is known as probably approximately correct reinforcement learning, coming over from the supervised learning approach, where we try to bound with high probability the number of mistakes that the algorithm makes. And again, in these cases, generally we'll be thinking about scenarios where these regret bounds and these probably approximately correct bounds are going to be a function of the size of the domain. Now, perhaps one of the easiest cases that we could imagine hoping to be able to try to characterize and achieve sort of limits on how well any algorithm could do is episodic tabular Markov decision processes, where we think of there being a finite set of states and actions, and that then the agent is going to interact for H steps and do that once, and then do that for a series of decisions. So that's the setting that we wanted to tackle, because even that had been open for at least 30 years. So if we look at algorithms, for those of you that may not work on sample efficient reinforcement learning, you might wonder if this is needed at all. Maybe all algorithms do pretty well, even under these formal metrics. What we can see is that if we don't have strategic exploration, we don't have algorithms that are trying to carefully quantify their uncertainty about how the world works and what that means for making optimal decisions. But in general, we can have bounds that are exponential in terms of the number of mistakes these agents might make, and that they might have linear regret, implying that they might continue to make bad decisions forever. Now, there's been an enormous amount of progress over the last 20 years, thinking about how do we make strategic reinforcement learning agents that can do much, much better than this. And a lot of what this work has involved is trying to think formally about the uncertainty over the models. And I'll talk more about that in a second. So at this point, together with my former student, Chris Dan, who graduated from CMU a few months ago, we now have closed this problem. We now have tight upper and lower bounds for episodic tabular RL for both of these important metrics for regret and PAC. But when we looked at this, there was something that was still not very satisfying about it. Because even though in some ways it is wonderful to be able to characterize how well a reinforcement learning agent will do on any domain and have these tight bounds, it was clear that in some cases we could do much better than this. So we know that in certain classes of decision processes, they might be very much easier. So a bandit is much easier than a reinforcement learning agent. The deterministic systems are easier to learn in. And it seemed like that we knew that in some cases, if there was structure, that we could do much better than these generic bounds, but that required us to know that structure in advance. And if we want to be able to democratize AI, we have to have algorithms that are going to work really well, regardless of whether the user is a PhD from CMU or from Stanford in our subtopic. And so together with my student, Andrea Zanetti, we started thinking about how could we have generic algorithms with instance-dependent bounds. So in particular, how do we have an algorithm that can work on any reinforcement learning problem, in this case, episodic still, but is provably going to do better if there is particular structure in the domain. So let me be a little bit technical about how we accomplish this. In order to make progress on this problem of how much data does any agent need to learn to make good decisions, one of the big insights has been to develop formal models of uncertainty over the dynamics model, models of uncertainty over the reward model. And one of the beautiful results in this area is that by being optimistic with respect to that uncertainty, that we can create strategic agents that learn very quickly. And the way in which this sort of uncertainty is quantified and used to make optimistic algorithms historically was done by building up models and uncertainty over, say, the dynamics model parameters and separately over the reward model parameters. And we would use things like Hofting inequality, standard concentration inequalities, to bound this uncertainty. The problem with using this type of approach is that it's not very tight. And so one of the different approaches is to say, instead of thinking about the dynamics model separately from the reward model, let's try to get better quantification of our uncertainty over what will be the result of particular decisions by using tighter concentration inequalities. And in particular, by doing this, it reveals that one of the important aspects is what is the variance of the value of the next state under the optimal policy. And it turns out that this quantity is really critical for quantifying how hard it is to learn to make good decisions. So essentially, if there could be a huge range in the value of the next time state, some states might be really good and some states might be really bad, but that variance means that it's going to be much harder to learn in. And in fact, this was a quantity that was proposed by Shai Menor and some of his colleagues a few years ago, but it wasn't yet known whether or not this actually could lead to stronger results. Could this lead to sort of instance-dependent results? And so what our work showed is that, in fact, our regret bounds for this setting depend on this variance of the value of the next time step. And what does this allow us to understand? Well, it enhances our understanding of knowing when it is hard to learn to act well. So in particular, our results help uncover some of these domains which are known to be easier to learn in. One example of this is deterministic Markov decision processes. If your domain is deterministic, you only need one sample to learn the dynamics model from a particular state. And in this case, it is well known that you should need much less data in order to learn to act well. And our bound automatically recovers that, a near tight bound for that setting, showing that in those cases, the variance of the value of the next time step has to be 0 because there's only a single next time step. On the other hand, we can think about bandits, where we only make a single decision and where the state of the next time step is not influenced by the decisions that are made. Another way to think about this is where we have extreme stochasticity in the dynamics model, such that in fact your decisions don't impact the next state. Again, in this case, it is known that we need less data to learn to act well, or it's known that regret is much better. And our results, again, recover that by showing that the variance of the value of the next time step is also much smaller because of this structure. And it turns out that really the hard case for when we need a lot of data to learn how to act well is this kind of in-between, where you have some states with very high value and some states with very low value, and the possibility of reaching both. And this algorithm, in addition to sort of giving us an understanding of when is it hard to learn to act well, it helps answer a recently posed question in the learning theory community, which was arguing about how much harder it is to learn to make decisions if your decision process is much longer. And our work helps answer a core part of that question, showing that in fact it is not harder to learn to act well in longer horizon problems for their definition. It also provides a way to solidify and understand the foundations of the previous empirical findings of past work, which had shown that this sort of variance of the value of the next time step seemed to be correlated well empirically with how much data was needed to learn to make good decisions. So I think to summarize this part, this is one example of how by thinking about what are the limits of how much data we need to learn to make good decisions, that we can not over sort of solidify the foundations of some important questions in our field, but we could also start to build our understanding of why is it hard to make good decisions in some cases and not in others. So again, I didn't have a chance to talk about a lot of our other work in this area, including a lot of work we've been doing in lifelong learning and transfer learning, but feel free to ask me about that later. I'll pause for a second in case there are questions and I missed them, because I can't monitor the chat right now, but I'll keep going unless I hear from you guys that I should pause. So the second thing that I want to talk about is how do we learn from limited samples to robustly make decisions? So one of the most common things we do in reinforcement learning is we do what we call off-policy reinforcement learning, where we use data from one policy to learn about the performance of another policy. This is what we do in Q learning. This is what we do in the vast majority of reinforcement learning. And the reason this is hard and quite different than supervised learning is because of covariance shift. Because we think that when we have different policies, different mappings from states to actions, by definition, they're going to be making different decisions in parts of the state space, and therefore they have to create different state distributions. So I put up here a figure I like a lot from some of my colleagues over at MIT and Harvard, looking at what is the distribution of sort of patient states you reach by making a sequence of decisions. And what their point is in this illustration is to argue that over time, depending on the decisions you make, you will have a different cohort of patients. And this introduces a lot of technical challenges. And indeed, off-policy reinforcement learning since 1989, 30 years ago with Q learning, has been studied extremely extensively. And if your domain is tabular, like the domains I was talking about before, where you can exhaustively enumerate and write down the value for each state, off-policy reinforcement learning tends to work fairly well. But it's been well recognized for a long time now that as soon as you start to think about really complex state spaces and infinite state spaces that are often going to be necessary for a lot of the problems we want to tackle, that off-policy reinforcement learning, when we think about using that with function approximation, starts to have a lot of challenges. And there's some very well-known divergence results from the 1990s, where we start to try to do off-policy learning with function approximation. And so to try to tackle this, there's been this extensive amount of work on how do we have sort of reasonable objectives for off-policy reinforcement learning. One of the most common ones focuses on projected Bellman error. I'm not going to get exactly into the details of Bellman error now, but essentially here it's leveraging the Markov structure and trying to say, well, if we know the Markov structure is present, then let's leverage that and try to create this sort of particular loss function that we're going to optimize. And this has really been the dominant focus of a lot of that work. And I think that that makes a lot of sense if you're thinking about domains which have tended to be addressed, like robotics, like video games, where we're creating the models of the world. So we know exactly what the state space is, what the action space is. We're often writing down the dynamic model or have access to a simulator of it. And so places where we can be fairly confident in our model approximations or in the fact that the domain is Markov. But in the cases that I think about, we're often going to be limited in our data, and we're not necessarily going to have known model structure. So in particular, in contrast to a lot of this prior work, which has thought about cases where you are doing off-policy learning, but you may also have the ability to continue to gather data, in the cases that I think about often, we're going to be really restricted to batch reinforcement learning. So at the top here, I've put up an example from our collaboration with War Child, which is an organization that supports children in conflict regions. And one of the things they do is they provide educational technology to those kids to help them learn if they don't have good access to formal schooling. Now, in many of those cases, they don't have Wi-Fi, and they will not be able to update that software for months or even 6 months in order, so students will largely be using a system that's static for a while and then can have periodic updates. And so it's crucial that we can use the data in those cases in order to figure out what will work well before we deploy it. Similarly, in healthcare, we often have access to data where it is not trivial to do online modifications. We're going to want to use that prior data. And so what I would argue is that if we're going to be thinking about these types of applications, that we want to think about different objectives. And so this figure, which is from Sutton and Bartow's famous reinforcement learning book, is to think about another objective that has not been focused on much, which is value error, which is really thinking about how different is our estimate of how well a policy will do compared to how well it will actually do in the real world. And so this is just a different objective, and I think it's an objective that we should pay increasing attention to if we want to move and use reinforcement learning for these other types of applications. And in particular, we're often going to want to do this in a way where we get robust, good assurances on how well will these policies do before we actually deploy them. And we might want to do this both for things like evaluation, where we have a particular decision policy we're curious about figuring out how well it does, as well as for, oh, I see that some of the formatting got messed up, but so it goes. And also for policy optimization, where we're trying to make decisions about which policy we want to deploy in the future. So I'm going to talk to you about one of those examples. And again, just to be precise here, I'm thinking about the scenario where we have batch of policy reinforcement learning. We have access to data from a particular behavior policy. And one approach to this is to do off-policy Markov decision process RL on that data. We can do things like Q-learning. You could do deep Q-learning. There are many existing off-policy Markov decision process RL algorithms that you could run over your batch data set. One of the challenges that we encountered when we did this happens to be a model-based approach, but it's not restricted to that, is that we could build up cases where, for example, in this case, we were looking at building up different sort of models and then comparing different models for an educational domain and then using it to compute policies. But what we found is that, and this is in black, that the performance of those policies, even if we had better models of the environment, weren't necessarily leading to better rewards, better actual policies. And really the challenge here is that we have bias due to model misspecification. This is an educational domain. It was almost definitely not Markov, and we almost definitely did not have a perfect model of student learning. And so this is one of the big challenges, is that in the cases that I think about, in many important cases, we're going to have huge model misspecification. So an alternative that many people are probably familiar with, but just as a quick refresher, is importance sampling. Importance sampling allows us to take Monte Carlo techniques and use them when we have data collected from a different distribution by reweighing it to compare the probability that we would have seen that data point under our new decision policy versus our old. And so this was extended to reinforcement learning by Doina Prekop and others about 20 years ago. And one of the nice things is that it doesn't require you to have access to a dynamics model. You can just use samples directly, and it's an unbiased estimator. The problem with this is that it can be very high variance. And in addition, we showed in a paper, in our best paper in UAI in 2017, that actually, even if you have these unbiased policy estimates, once you start to use them for making decisions, that can be systematically bad due to the large variance. And so a really natural idea that has been thought about a lot in the past is, let's combine these different forms of estimators. So in online learning, people often combine Monte Carlo estimators and Bootstrap or Q-learning estimators. And really, we can just think of sort of using these hybrid models where we have some sort of parametric or Q estimate with some importance sampling estimate that has high variance. And what we wanted to do in this case is to think about, there'd been a lot of algorithmic work in reinforcement learning, thinking about combining these different approaches, often some empirical success, sometimes some failures. But the theoretical analysis tended to assume that we were really in a Markov setting, but not dealing with challenges around model misspecification and focusing on these other loss functions I mentioned before. But fortunately, from the statistics community, there are doubly robust estimators that provide us with a formal way to balance between these two. So in particular, they allow us to combine estimators that might be biased with importance sampling estimators. and they allow you to get models that are going to get estimates that are consistent, either if the model is consistent or you can know what the behavior policy is, you know what the probability was of taking actions. And these have been studied very extensively in other communities, including the bandit community, but there's been relatively very little work for multi-time step processes. And so together with my former postdoc, Phil Thomas, we were really interested in this question of how can we be data efficient and get good estimates of how well a new policy will do before we deploy it. And our intuition, again, was to focus on this value error estimate, that we really want to know how good things are before we actually deploy them. So in particular, we introduced two different forms of ways of doing policy estimate. One was thinking about a weighted importance sampling variant of a doubly robust estimator. And from those of you that are familiar with importance sampling, the weighted version is known to often have a small amount of bias, but has much less variance. And empirically, it can often give much more accurate estimates. The other one was thinking about how do we try to formally combine between these high variance and high bias estimators. And in particular, we can think about blending. So we can have some types of estimators that have, maybe that mostly focus on a Q function and only use a little bit of importance sampling, and other ones which mostly rely on importance sampling and only use a little bit of bootstrapping, and then a whole amount of blending in between. And what our idea was is that we really have access to all these different types of estimators, which we can think of as sort of being off-policy end-step estimators for those of you that are familiar with that. And the question is, how do we balance this? And what we thought is, well, what we'd really like to do is we'd like to get good mean squared error. We'd like to get highly accurate estimators by balancing between these two. And to do that, we formulate this as a quadratic program. We're trying to directly figure out how to balance between these estimators in order to support good performance. Now, for those of you who are familiar with sort of thinking about these, you might immediately say, well, how are you going to get estimates of the bias and the variance of these types of estimators? Well, the variance turns out not to be too hard. We have access to a sample covariance, but bias is really the difference between how well we're predicting a policy will do and how good it actually is. And if we actually knew what the bias was, then we would know what the true policy value is. And we don't have data about that. So we don't have a good estimate of the bias. We have to figure out a way to estimate this. And the insight that we had is that one of the beautiful things about importance sampling is that it gives you an unbiased estimator, but there are also ways with standard concentration inequalities to get confidence bounds over that estimate. So importance sampling will give us one estimate of how good a policy is. And then we might have another estimate from our model or our Q function. And the nice thing is we can look at what those confidence intervals are over our importance sampling estimates. And what that implies is that we get an underestimate of the bias. So if the Q function lies outside of that range, we know that it at least must be biased with high probabilities by that gap, because we know that the true value has to lie within the confidence intervals of the importance sampling estimate with high probability. So the nice thing about this is it gives us a way to get an underestimate of the bias. What does that imply? That implies that we're going to be slightly favoring the model compared to, we're going to over use the Q function estimate compared to importance sampling. The reason why we made that particular design trade-off is that we had found empirically that many of the estimators using Q functions often were quite good, even with the model misspecification, because they have much, much lower variance than other approaches. So this is how we can use an estimate of the bias to solve this quadratic program. And what we could also show in this case is that we had the first proof that these doubly robust estimators, that they're strongly consistent, meaning that with infinite amounts of data, we will converge to the true values under mild common assumptions. And I think this is really helpful because this is showing us that for this, in some ways, a much harder objective of saying we want to look at really what is the distance between what are we predicting and what is the true value, that we can have access to techniques that give us sort of the minimal assurance of saying that yes, if you get more and more data, you will be guaranteed to get a good estimate of that policy. And so that gives us some sorts of formal assurances that we're going to get things that are good. Now, of course, from an empirical side, it matters equally whether or not it works and whether it buys us any benefit. What you can see here is a simple domain. It's a grid world simulation. And on the x-axis is the amount of data that we have. So it's a log scale, going up to 20,000 trajectories from some behavior policy. And what you can see here is that, as we might hope, most of the methods keep improving with more data. You can see here that the model that we're using eventually flatlines. That's the black line here. And the reason that it flatlines eventually is that the bias dominates and it's not improving anymore with additional data. So perhaps unsurprisingly, because I'm showing you this result, our approach of magic is the best. It's got the lowest mean squared error for the amount of data. But I think what was much more exciting to me and important is that let's look at how much data we need to get a good estimate of the policy value. What you can see here is that we're being about 10 times more data efficient for this domain. So that with 10 times less data, we can still get a good estimate. And I'll give you an example in a second of why that can be so important. So other people have built it's exciting to see that there's been a lot of follow-up to our work. And one of the application papers that tried to use one of our estimators, weighted doubly robust, was using this for a sepsis treatment example. In this case, they had access to approximately 20,000 patients. And what they wanted to do was try to see if they could do batch reinforcement learning to identify if there might be different treatment decisions that could further improve patient outcomes. Now, what they found in this case is that if you used a number of different forms of techniques for estimating how good these alternative policies could be, our weighted doubly robust estimator was the only one that could provide these tight enough confidence intervals over the value of the different policy that you could have some confidence that it might be better than the standard policy. Now, I want to be careful here. This is under some important assumptions. You'd want to do a lot more work before deploying any of these types of policies. But what this illustrates is that the type of technique you use to do off-policy batch evaluation matters, and that if you have more data efficient methods, then you can use these in cases where you really need to be confident about the improvement. I think another thing that I found surprising but exciting is that this work was published around 3 to 4 years ago, but yet there was a recent bake-off comparing a number of the different forms of batch off policy reinforcement learning, and our magic algorithm still has state-of-the-art performance in a number of important settings. Again, focusing more on sort of these data efficient scenarios and scenarios where you may have model specification. Now, before I conclude this part of the section, I just want to address a question that might be lingering in some people's minds, which is I'm arguing that there might be this enormous opportunity for leveraging trajectories of decisions made and outcomes, and that we might be able to do better than imitation learning, where we just try to be able to learn to match previous decisions that are made. And one reason I'm so hopeful about this is from one of our earliest results in this, where we're looking at data that was gathered randomly for an educational game. So we had access to about 11,000 learners' trajectories. We're trying to learn a policy that increases student persistence. And in this case, you can get policies that depend on how much time the student is spending in a level. And we found by doing this form of batch off policy reinforcement learning, we could improve over the current behavior policy by over 30%. And so that illustrates to me that there really is an enormous opportunity for these types of techniques to try to quickly learn from limited data in order to make better decisions. And there's an enormous amount of future questions that we're currently working on, and I think there's a big opportunity for the field. Okay, so the third thing that I wanted to talk about is to return to this question of what is a good decision. And really throughout this talk, I've been focusing on the sort of standard thing of what we use for our objective for reinforcement learning, which is expected discounted sum of some scalar reward. And I've told you how we could optimize this with and evaluate it in terms of regret or in terms of PAC or in terms of empirical performance. But I think it's important to acknowledge whether that's really the right thing that we want to be optimizing for. Reinforcement learning broadly as a paradigm could allow us to have continually improving systems, to help us to do better. And I think it's really interesting to think about what are the types of objectives we want to achieve. And so for the work that we've been doing on that, we've been trying to think really hard about what is the objective we want these sort of automated systems to be helping us with, and to think about the complexity of the objective, to auto-diagnose if we have inadequate performance, and to think about how do we design the decision spaces to support good outcomes. So we've been doing a lot of work in all of these areas to really think about these different types of challenges. And I'll talk briefly about two examples in this space. So recently, we had a paper looking at how do we prevent undesirable behavior of intelligent machines. And this is really one step towards thinking about how we can tackle complex objectives. And in particular, what we are arguing here, and I think of this particularly for the reinforcement learning setting, is that in many cases, we don't care about just a single expected scalar reward. We also care about constraints. We care about constraints to do with equity, to do with fairness, to do with safety, and that we would like to often have assurances that our algorithms will produce solutions which are going to satisfy those constraints in the future. Now, we introduced some algorithms here. I don't think they're optimal. I think they're a first step towards trying to tackle this sorts of domains. And there's a number of other people who are working really hard on this challenge as well. One thing that we found is that this framework already was useful for us to think about a diabetes insulin management problem. We had access to a simulator that was approved by the FDA to replace early stage animal trials, to think about what sort of insulin dosage do you use to help people with blood glucose control. And one of the things we could show in this case is that if you want to be careful about hypoglycemia while still trying to optimize for another performance metric, that by using our algorithm, it could decide when to switch to a better policy, and that the amount of data that it needed to do that was reasonable. So that for an individual patient in this simulator, within about 4 to 5 months, our algorithm could find a policy that it was very, had high confidence would do better and satisfy the desired constraints. And that this did much better compared to prior algorithms, which typically only try to optimize for one objective. So that's just one instance of how we can start to think about these more complex domains. And we've been doing a lot of other work on this. And I think there's a huge amount to be done to think about the sort of really rich set of objectives we'd like to tackle. I think one thing that I've noticed a lot in my applications work is that we don't always start with the best system definition. And this perhaps shouldn't be surprising, particularly for anybody that's ever worked on a product. We rarely start out with a system that has the perfect state space, has the perfect action space, and all we need to do is optimize it. And so we thought a lot, including in the theoretical side, about how do we figure out when the system isn't good enough, and also how do we work with experts to figure out what should be the decision spaces. If we don't have good actions, we're not going to be able to achieve good outcomes. Let me give you one example of some recent work on this together with some HCI colleagues. And this had to do with a case we're looking at for education of how do we help people better learn facts and definitions. Fact and definition learning comes up all over the place. I put up Duolingo, which of course was started by Louis Van On at CMU. There's an enormous amount of fact learning for language learning, but there's also an enormous amount of fact learning in lots of disciplines. It's often sort of a beginning prerequisite you need to start learning about a new area. And the dominant paradigm for quickly learning about many facts is the flashcard. There are literally thousands of research articles about using flashcards to help people learn things. And there's been an extensive body for many decades of research that looks at how do you adaptively sequence these items to help people remember these things using models of human memory, using human subject experiments. And one of the beautiful things now is that with our phones, with our computers, it's really easy for these algorithms to be implemented seamlessly. And so we can all take advantage of this, decades of research of how to help us best learn fact-based knowledge. So you might think that this is something where we've sort of solved this problem. We have really great algorithms, it's been studied for a really long time. The problem is that most of this sort of fact learning typically happens outside of the classroom. And flashcards are tedious. Most of us don't think on a Friday night that our favorite thing to do is to go home and study a whole bunch of flashcards. And so we were really interested in thinking about how do we help people learn these in more optional learning environments. So at the same time, we've seen this incredible advances in natural language processing and a huge amount of interest in chatbots. There's now an enormous number of chatbots out there, and the technology is getting better and better. And so what we wondered about is whether we can combine sort of fact or definition practice with a chatbot. And so we created something called Quizbot to help people learn different forms of factual knowledge. And what we wanted to understand is how did that compare to using sort of a standard flashcard equivalent of the same material? And in fact, we even used exactly the same spacing algorithm for both of these paradigms. So we wanted to have things that in terms of the next item you were practicing, we were using a state-of-the-art algorithm to do that sequencing, but we wanted to change the interface to see how that affected learning and engagement. The experiment, we did a couple experiments, but the one I'm going to talk about today, we sort of start the students with a test, and then people can use the flashcard interface or the chatbot interface, and then we do another test at the end of 7 days. Now, people had to use the system a little bit each day in order to get paid, but there was sort of just a minimum baseline of how much time they had to use the system per day, and of course that was the same regardless of which type of system you're looking at. So what we found is that the chatbot used people use the chatbot system about 3 times more than when using the flashcard app. So even though it was optional, people were vastly just using this much more. Now, when Sherry Ruan, the lead student on this, told me this, I said, well, okay, great. It's not so surprising to me. It's a lot more fun and engaging. The question is whether or not that actually leads to learning gains. But importantly, people actually learned a lot more. So when we looked at recall accuracy, they learned substantially more than using the flashcard app. And this is an effect size of about 0.5. For those of you that don't tend to look at effect sizes, in education literature, it's very common to get no effect size or small effect sizes. Being able to get things like a medium effect size on something that's been incredibly well studied was really shocking to me. And I think it really underscored to me the importance of this combination of algorithms with the right design space, that by combining with experts in these other different fields, whether HCI colleagues or education colleagues, we're often going to need to design and change the action space itself, and that by doing so, we can get very large gains. So this is something that we've been continuing to think about, I think will be very, very important going forward. And what I've argued to you throughout this talk is that this question of how do we learn from limited samples to robustly make good decisions allows us to think about a lot of the different really important technical challenges that come up when we want to use RL for societal impact. And really, my ultimate goal is that I envision having these sort of continually improving human RL systems, where we're combining between human experts to try to have, change and modify the action space, the reward definition, and the state representation. And we have RL systems that are not only trying to optimize for those definitions, but then proactively reach out to people as they diagnose insufficiencies or opportunities for gain. And that if we do this, I think we're going to be able to create systems that are truly worthy of the people they serve. Thank you.